everyone. My name is Shaleen Jain, and I want to welcome you to our Monday seminars. Today we have Dan Coker, who's a spatial scientist at TNC's Maine chapter. He leads a team of scientists and practitioners and focused on a lot of exciting and diverse conservation issues. Dan has spent over 2 decades at TNC, previously at the Appalachian program, and now he's also involved in some work in the southern Andes. So, welcome, Dan.
Great. Thank you very much. So, let's see if I can get this all right. Can you hear me? Okay, great. So, today I'm going to be talking about tools that we create to help with conservation decisions, internal to the Nature Conservancy, and tools that we share externally with partners, government, federal government, municipal governments, and state government when they'll listen. So a big part of my job is creating science-based information tools for those who make decisions about conservation strategies, funding, and priorities. And when I say tools, the most common tools that I use, that I create, are things like GIS datasets, maps, web applications, and also all the interpretation that goes along with them. Specifically today, I'm going to be talking about a project that we're just starting with Shaleen and his graduate student Prashanta. And it's a project to map and attempt to quantify the ecosystem services of floodplains. So, sort of the sequence of my talk today. I'm going to give you a brief history of TNC, mostly TNC in Maine, that led to our interest in things like ecosystem services, specifically floodplain ecosystem services. I'll go into some detail about the current project I'm working on with Shaleen and Prashanta, and then I'll give you a few of my own observations about what help makes a good sort of science outreach tool. So first, a bit about TNC, big TNC. Most importantly, for this talk, it's really a science-based organization. All our decisions and strategies are based on the best science that we can find or work on ourselves. It's one of the largest conservation organizations in the world, and we protect ecologically important lands and waters for both nature and people. More than 1 million members worldwide, and it was founded in 1951. And since 1951, we've protected more than 119 million acres of land, thousands of miles of rivers, and we today operate more than 100 marine conservation projects globally. And so we work, there's a chapter of the Nature Conservancy in every state, but we also have programs in more than 70 countries. Okay, the Nature Conservancy in Maine. Founded back in 1956 by Rachel Carson and a small group of ecologists. It was the fourth chapter in the organization. And in 1961, Step Falls Preserve was the first piece of land we protected. And so Step Falls is a lovely little place, but it is, I believe it's 24 acres. So keep that number in mind. And the Nature Conservancy no longer holds this preserve. So aside from protecting lands that we permanently hold, we also protect lands and then transfer them to other conservation organizations. And this is now owned by the Mahoosic Land Trust, I believe. So it's a 24-acre preserve. So over our rich history of the last 62 or so years, we've done hundreds of land protection deals throughout Maine, protecting jewels like Great Wass Island down east, the Big Reed Reserve up north of Baxter. It's about, it's going out to you. 5,000 acres of it's the largest piece of old growth forest east of the Mississippi. To the landmark St. John River deal that we did, which was at the time about 185,000 acres. To the 41,000 acre Debs-Knegs Lakes Wilderness area south of Baxter. And the more recent Luthold Forest Preserve, which is about 17,000 acres near Jackman. So this is a map I made. It's a few years old, so then these numbers are a little bit out of date, but just to sort of give you an idea of the scale of the land conservation work we've done over the years. Currently, we own just over 290,000 acres in Maine. We hold easements, conservation easements on a bunch of land, and partnering with others, so land that we've protected either where we've acquired it and transferred it to other organizations or helped them protect it. We count, right now it's up to about 1.9 million acres in our history. And over the years, our land protection strategy has sort of evolved, where it was really, at first it was a sort of strictly philanthropic driven land protection, but today we employ all sorts of strategies, many of which involve influencing policy, public funding initiatives, and developing the science that supports them. So in 2006, we became a key partner in the Penobscot River Restoration Project. And our involvement in this project has led to a tremendous growth in our freshwater work, largely around strategies to improve river and stream habitat connectivity. And today our freshwater program they do some of the most exciting and innovative work in our chapter, I would say. And this is just a map sort of presenting the different freshwater strategies that we employ. Oops, sorry. So in 2008, we really got into the marine conservation realm and completed our first marine conservation assessment, the Northwest Atlantic Marine Assessment. And in the 10 years since, we've become really involved in marine conservation issues, mostly through our work in sustainable fisheries management, marine spatial planning, connectivity for diadromous species, so more on the river connectivity piece, and coastal resilience planning. So we know that all these systems are really integrated. There's not a clear separation between lands, waters, freshwater, marine. But we organize our work into these 6 categories these days. And we spend a lot of time, as I said, influencing public policy and funding for conservation, whether it's pushing for another Land for Maine's Future program, funding for culvert upgrades through the water bond, or administering the Maine Natural Resources Conservation Program. So today we're not only doing land and water protection work, but we seek to inform and influence the conservation work of others through scientific investigation and application. So as TNC has evolved, along the way we've made much more of an explicit focus on people and explicitly incorporating people into our conservation science and planning. One way we're focusing more on people these days is to identify, quantify, and demonstrate the services that nature can provide for all of us. These are termed ecosystem services, but you probably all know that. Whether it's obvious services such as clean water, fish, shellfish, recreation, or lesser understood services that habitats provide, including things like flood hazard mitigation that I'll talk about in just a minute. So as the climate changes and storms are becoming more and more severe and frequent, flooding will likely become more severe and frequent. We are therefore embarking on this project to investigate methods to map and quantify the natural services that floodplains can provide. Our first real foray into natural ecosystem services, sort of characterizing and quantifying, was back in 2013 in preparation for a campaign to pass the water bond, which passed in 2014. And this was a collaborative effort with Charlie Colgan at USM. And I did a bunch of work for this project, created a series of maps illustrating different types of ecosystem services. And sort of the roughest one that I felt we didn't have the best handle on was this flood attenuation service that floodplains can provide. So there was my brief history of the Nature Conservancy. And now the current project, and I want to say again that this is a project we're just starting, so I don't have results for you. I have more like, here's our current approach, but our approach is evolving a bit as well. So this is the sort of why we care, our goals and approaches. I'll talk a bit about our methods, and I will get a little bit technical in GIS land, but I will not go there for too long. And then I'll talk a bit about the next steps we have planned for this project. So what the heck is flood attenuation? I am not a hydrologist. I'm a GIS analyst and sort of a generalist. So please speak up and correct me if I say anything wrong about flood attenuation and my very sort of surface understanding of it. So it's this idea that, and we're specifically talking about flood attenuation by natural floodplains. So it's this idea that when a flood pulse comes through a system, if this is the pulse of the flood, attenuation means you're slowing, you have the same amount of water, but you're basically slowing the pulse down and chopping the peak off this curve and spreading that pulse over a longer amount of time. So what this can do is basically slow down a flood, reduce its volume a bit, and then why we care about this is it can actually lower the impacts of downstream flooding. So a city downstream of a big floodplain that's working can actually have lower flood effects because of the upstream floodplain. And if all goes well, I'm going to show you a portion of a really good video from Vermont, from Hurricane Irene, that explains flood attenuation and is a really nice example of the benefits of
Tropical
floodplains.
storm Irene slammed into New England in August of 2011.
I'm going to pause it before I really start. I want you to try and guess who the narrator is. And I will give you a hint. So this is Vermont, and he does not yowl on this video.
And nowhere was the devastation more widespread or severe than in Vermont. The people of my home state lost more than Vermonters had in a generation. Irene damaged more than 500 miles of roads, 1,000 culverts, more than 200 bridges, and 1,600 homes. The most unfortunate loss was the Vermonters who lost their lives. However, some places fared better than others did. Some bridges and culverts stood while others nearly succumbed. Some towns had little damage while their neighbors suffered much more. Partly, those were accidents of fate, geography, and weather. But there's more to the story than that. Choices made in some communities long before Irene arrived helped provide some protection. Take Middlebury, where Irene floodwaters rushed through the town's iconic stone bridge for many days after the storm. But those Otter Creek floodwaters were slower to rise and fall and had far less power than they did just 30 miles upstream in Rutland. The reason was the protection and the preservation of riverside floodplains and wetlands. And that was due to a difference in how the people who lived along the river think about and deal with the Otter Creek.
We have a set of gauges in Vermont that measure the amount of flow that's going by, the flow that's produced in the watershed that flows into that given point. These gauges measure the amount of flow. In Rutland, we had somewhere in the neighborhood of 14 or 15,000 cubic feet per second that was going down the Otter Creek at that point in the watershed. We would expect, as the river flows down its watershed and the watershed size continues to get larger and larger, that flow would also correspondingly go up. Here in Middlebury, we were seeing a flow rate of somewhere in the neighborhood of 8,000 cubic feet per second in Middlebury. That's a halving of the flow that we were seeing way upstream in Rutland. So instead of the flow of the river rising as the watershed size increased, we actually saw a dramatic decrease. If the flow is reducing that much, that water has to go somewhere. And where it was going was spilling out of the Otter Creek onto the very large floodplain and wetland complexes that you can find between Rutland and Middlebury.
We can't say for certain that the Main Street Bridge in Middlebury would have been damaged during Irene if there hadn't been this vast complex of floodplains and wetlands above it. But we do know that there was a good chance of that. The likelihood is very high that there would have been some damage. It's hard to tell how much it would have cost if the floodplains and wetlands hadn't been there and there had been more damage. But we can say that without those natural flood protection mechanisms that nature provides, there would be more damage, and of course it would cost more to rebuild.
Otter Creek Swamps is the largest forested swamp complex in all of New England. This swamp complex extends from the southern edge of Brandon to the southern edge of Middlebury. There are 8,700 acres of forested natural communities, some of it's swamp, some of it's floodplain forest. It's a whole mosaic of 10 different natural community types. The natural process that makes this landscape tick is flooding.
One of the really important functions of wetlands is that they retain floodwaters, and part of the way that they do this is by letting the water come up, and then with all the duff layer and the irregular surface, it holds the water a little bit, and the ground gets saturated, and then the water slowly goes down, where the river has access to the floodplain when there's wetlands in there, and those hydric soils really hold on to the water quite a bit. So in the case between Middlebury and Brandon, there's a pretty extensive wetland complex in there, and those wetlands absorb that floodwaters as they come screaming down the mountains and into the valley bottoms. And in instances where you don't have that type of a wetland complex, the waters scour and pick up velocity, and the more they scour, the more sediment they pick up, and the more sediment they pick up, the more erosive force they have. So it just becomes cumulative down the watershed instead of attenuating some of those impacts of velocity and the volume as well. So putting those wetland complexes in between is like putting a release valve in the system. Vermont and the country have a no net loss of wetlands policy, but in reality we just haven't seen that every day when there's more and more wetlands. Unless
All right, I'm going to stop it there. But pretty dramatic, that reduction between Rutland and Middlebury from, what they say, 14 to 15,000 cubic feet per second to 8,000 cubic feet per second. So it's sort of the best especially in the Northeast, best example of real-life flood attenuation that I could easily find out there. So, onto our current project. So, we don't have a huge system in southern Maine, at least, like that Otter Creek. They were talking 5,000 or 6,000 acres of swamp around a river that floods regularly. But we wanted to investigate sort of whether we could use existing publicly available GIS data to develop methods to quantify and then sort of highlight this flood attenuation function that floodplains that are in good shape can provide, and then, as I said, effectively share that information with stakeholders and decision makers. And I'll say again that we are in early stages of this project, and these are just sort of off the top of my head examples of potential users of this floodplain attenuation information. So I was thinking conservation planning and prioritization for land trusts. So if you can point out important floodplain wetlands that are in need of protection or restoration for a land trust, we could maybe build it into the Maine Natural Resources Conservation Program criteria. So that's a funding program. And then, so there was a wetland protection portion of the original water bond. It was a pretty small fraction of the money, but if there's another water bond, it could be a larger fraction, and some of that could go towards floodplain protection. Okay. Sorry about that. So once again, the who of the project, Shaleen, Prashanta, Dave Kornemunch in our office. Many of you probably know Dave, and myself. And not saying who's who of the four of us, but I'm probably the tallest, so I'm going with Pete Townsend for myself. We haven't had that discussion yet. So along the way, we're planning to not do this project in a vacuum. We're planning on engaging with potential users and stakeholders in this project who might include the Maine DEP. We've had a meeting with the Cumberland County Soil and Water Conservation District. I was thinking another state program, the Maine Natural Areas Program, and then we're still working on others as we sort of evolve our approach here. So our proposed, in parentheses approach, is to accurately map and model floodplains using high-resolution elevation data in 2 pilot watersheds. And these 2 pilot watersheds are going to be in southern Maine. And so number 1, that's my department. Number 2, model and quantify the flood attenuation potential mapped in these floodplains that, the flood attenuation potential that these mapped floodplains could provide to downstream communities, and then determine the key intervention points that influence attenuation services. So by key intervention points, I mean the places where we can make a difference, where we can improve the attenuation service of those floodplains. Whether it's maybe it's a floodplain whose the lateral flow might be restricted because of some bad culverts that could be upgraded to improve that flow, or other restoration, or perhaps conservation. And so after modeling and quantifying, identify are there key places in these watersheds that are in need of protection or restoration, and then it would be great if we could create a web-based tool to share the results, but also really provide strong and straight-up guidance on how to use the information. So, back to number 1, accurately mapping and modeling these floodplains using elevation data in these 2 pilot watersheds. So I'm going to go into this a little deep, but I will try to keep the acronyms to a minimum if I can. So all of our mapping here, the modeling of these floodplains, that I'm going to talk about is based on really high resolution elevation data that's derived from LiDAR. And I want to give the Maine Office of GIS a shout out for leading the charge on getting LiDAR-based elevation models for the entire state. So within about a year and a half, this map shows what's currently, or almost currently, this is purple is the only stuff that's not currently available that will be available later this spring. And then the white, we just signed a grant agreement with the Maine Office of GIS. TNC is providing a small amount of the funding to match funding that USGS is providing to the Maine Office of GIS to get this information. So within a year and a half, maybe 2 years, we'll have statewide LiDAR coverage, which is pretty amazing. And not many states can say that. So I'm going to talk a little bit about the where of the pilot work I've done so far. And it's the lower Presumpscot River watershed down in southern Maine. It's about 130,000 acres. It's a nice mix of forest, ag, and down in the southern parts of the more coastal parts of the watershed, quite suburban and grading into urban. And we chose it because there were 2 significant flood events in the last 20 years. So flooding is a factor in this watershed. All right, zooming into an air photo of the watershed, you can see, as I said, up in the sort of northern reaches of the watershed, it's pretty darn forested. Into here, in the western, southwestern, there's a lot of ag grading into suburban, and here's Westbrook down here in Falmouth. So for the remainder of my sort of GIS method slides, I'm going to be concentrating on the area in that little red box. So the basic steps that I follow to develop a high-resolution, accurate floodplain map. So the big one here, that in big red letters, create accurate flow lines. So in order to know where the floodplains are and get a good, accurate map of them, you really need to know exactly where the water flows across the landscape. And this presented the first challenge right off. So the trouble, one of the troubles, so this is incredible data to have, as I said, and it's 2-meter resolution, so you picture pixels that are 2 meters squared, and the vertical accuracy is about plus or minus 7 inches. So it's incredible data, but it's new and it comes with its own set of troubles. So, let me back up. So there's a photo of this little sample area. You can see where the river comes up to the road. There's a pair of double culverts. The river passes through. Well, the LiDAR, so LiDAR is generated from an airplane, pulses of lasers bouncing off the earth. The LiDAR can't see those culverts, right? It doesn't know the water goes under the road. It sees the surface of the shrubs here. It sees the surface of the road, the sort of berm, and then down. It doesn't know what's going on underneath the road. And you can see that right here in that elevation data. So here's the thread of the river, gets to the berm of the road, and you can actually see the little bump outs where the culverts are, just to give you an idea of the resolution of this data. But if you're trying to create a flow model for this river, you know, where does all the water come into it, and then where does it go as it's growing downstream? It gets to here and it stops. So this seemingly simple problem took me about a month to solve. And I ended up developing a method to search the entire elevation data set, find all these places, and fix them, basically by cutting culverts in the elevation data. And so here's a picture. This blue line is my corrected flow line after applying this method that I developed. It was a major detour from the project. This yellow line shows what the flow line would have looked like had I not applied this method. And I don't think I'll go into any more detail on that. But it sort of involved, the water, you can sort of imagine the flow hitting the berm of the road and stopping and not knowing where to flow to next. And so you get these weird patterns that back up through the entire system, not just at the culvert point, but you can see it kind of messes with the whole flow line all upstream of that and downstream as well. Although that downstream jigger-jagger stuff is probably caused by a culvert here. Okay, moving on. So after I solved that problem, and we're zooming back out, so this is Falmouth, Route 95, and the Falmouth Spur Highway. This is a recent air photo. You can see the Presumpscot River sneaking through here with some pretty nice forest, at least for Falmouth. Here's the digital elevation model from LiDAR, and it's almost artwork. I mean, to me, it's so intricate, and it's almost like it's got a design to it. And you can sort of see, the way I've shaded it here, you can sort of see the floodplain of the river popping out already. So from that digital elevation model, the next step is to develop a slope model, because slope is very important in the shape of the land, which creates the floodplains. So this is a slope model showing slope. It's just darkest green is flattest, up through light green, yellow, orange, red is the steepest. From that slope model, you then can develop, and there's no legend for this map, I apologize. Looks like a soap bubble. It's actually flow direction. So for every pixel in your raster data set, it gets coded with which direction it drains to. So this pixel knows that it flows that way. This pixel knows it flows that way. And then, so this is really just colorized by direction of flow. So once you have direction of flow, you can create a flow accumulation from which you can actually derive flow lines of flow. So this is showing different size. So these are smallest headwater streams draining into larger streams, draining into the large river. And this red is sort of a mid-sized stream. And basically, you run a flow accumulation for your whole data set, and then set thresholds that you think are ecologically important. So at least 20,000 cells have to drain into a cell before it becomes a small stream. And then you set thresholds, at least 100,000 cells have to drain into a cell before it becomes a size 2 stream, up to a size 4 river, which is the largest in this watershed. So from the flow accumulation that creates these flow lines, so this is it, the flow lines overlaid back on the actual digital elevation model. You create a cost surface using the slope and the flow lines. You create this cost surface to basically represent how far the water from these different sized streams and rivers can push out during a flood event. So the cost surface is based on slope. So if it's flat for a really long time, you're going to get a nice wide floodplain. But if it's pretty steep right around the river valley, you'll get a more narrow floodplain. So you set thresholds, as I said before, for the different size streams and rivers, and you set cost surface thresholds for those same different size streams and rivers. So it's a pretty simple concept. So smaller streams, less water, less power to push up slopes, and then the bigger rivers have higher cost thresholds in this surface, so they can push out farther. And so I've written a series of scripts to do all this, and you basically, using the scripts, you can control those thresholds for cost surface for different river size, but you can also control absolute elevation gain in a flood for every river size. So there's this slope-based factor, but then there's also, we can say, rivers of this size will only rise 10 feet during a 100-year floods event. Anyway, so you run those cost surfaces for all the different size streams, combine them, and end up with a final modeled floodplain. And so I've been talking a lot about thresholds. How do you come up with these thresholds? Do you just sort of make them up, or is there some real world data you can verify them with? So the first time I ran it, I sort of just made them up based on other work I had done. But, and that's all sort of, it's the sort of thing where, like, here's step 1, 2, 3, 4, 5, 6, and you can go through 24 steps to create your floodplains. And you don't have to think a whole lot about calibrating them at that point. It's just sort of, I need to do this, then this, then this. The tough part here is trying to calibrate these floodplains to make them match reality. So what did I use? And so what you do is try to find existing data sets or photos from a flood that will help you calibrate your modeled floodplains to some sort of reality. And so what I used for this calibration was the FEMA flood hazard maps. And when I mention those, you might say, well, why didn't you just start with those in the first place? Why'd you go through all this modeling? Why not just use FEMA's flood zones? The answer is they're really inconsistent across the state. And they're especially lacking on the smaller sized streams, which can be important for this and for other conservation reasons. But for parts of this watershed, they're pretty good. And so they were a useful tool to help in this calibration of the modeled floodplains. So this is what they look like, the FEMA flood zones for this area. You can use, if there are flood gauges, so gauges, as the gentleman in that Vermont video spoke of, those flood gauges that measure flow. They also measure, they also can measure elevation change during a flood. So they'll say the river at this point in Westbrook got up to 16 feet above its normal gauge stage. So you can use that to calibrate your cost surface and your elevation change for different size rivers. The issue is, for this entire watershed, there were maybe 2 flood gauges that I could use. So you sort of say, all right, there's a flood gauge on this river at this, where it's this big, and use that to calibrate other rivers where they're that big, but there's a whole range of river sizes, streams in this watershed that we don't have good gauge information for. The other data set that I was lucky enough to find was an actual report from the 1996 flood event that happened in this watershed. And it was this really great report where they had actually gone out towards the end of the flood event and surveyed the elevation of the sort of terminal flood elevation at a bunch of different points throughout this watershed. So I could say, right at this place, the river got up to this elevation during this flood. And it was a really handy data set to have. I'll show you how to use it. So here's my originally mapped and modeled floodplains. Here's the FEMA data that I used for calibrating. And these points represent some of the locations from that report on the 96 flood. And what I did was just create little elevation data sets around each of those points that showed where the water got up to, basically, in that 96 flood. And this is the the floodplain that I ended up with for this area. And the way this calibration works is it's tiring. So it's the sort of thing where you look at data in one place in the watershed, tweak a bunch of numbers, rerun this script that would take 12 or 15 hours to run to remodel the floodplains, and have a look at the results. And what I would do was sort of set up spatial bookmarks all around the watershed to see, oh, how does it look here, how does it look here? And it would change things here in a good way, over here, not such a good way, and you'd sort of go back and forth until you settle on a place where you're not getting any more sort of positive change in this calibration. But this 96 flood data honestly helped a ton with calibrating this model. And I'm pretty pleased with the results, and I'm working on, Prashanta, I'm working on one more run of the model before I give you the data. Okay, so once you have these modeled floodplains, and you're sort of semi-satisfied with the modeled result, you can, because this elevation data is so high resolution and so accurate, it's pretty easy to start estimating the depth of flood. So this is depth of flood at a 100-year flood event for this place. And it's, sorry, no legend again, but it's shaded. The lightest color is the shallowest, to the darkest blue is the deepest. And then it's a sort of short walk to flood volume. And again, this is sort of lightest yellow up through blue, orange to red. And so I just wanted to show you a bit of, this is another sort of shout out to LiDAR data. So I wanted to compare a Nature Conservancy regional active river area data set that we did a bunch of years ago for the entire eastern region of the US at 30 meter pixels. So these pixels are 30 meters by 30 meters. Same sort of process to develop floodplains. So here's this place compared to the LiDAR-based data. So next steps, I'm going to hand this GIS generated data over to Prashanta and Shaleen for sort of further validation of the floodplains using actual hydrologic modeling that incorporates time and flow. And then I'm going to be working on developing these same modeled floodplains for a second watershed, and we're sort of in the process of determining what watershed that's going to be. It'll be another watershed likely in southern Maine. And then Shaleen and Prashanta again are going to be working on methods to develop and evaluate the attenuation benefits of these modeled floodplains. And one idea we had was sort of running floods through the model and experimenting with sort of removing certain floodplains from the watershed and seeing how the model responds as a way to sort of quantify the overall contribution of different floodplains to the downstream attenuation function. And then highlight some most important floodplain areas if some arise. So back to our overall approach. As I didn't come out as grayed out as I'd hoped, but those two middle are. Those are grayed out. I said I was just going to wave my arms around and magic would happen with Prashanta. And then I would step back in and we'd work on sort of publishing this data to the public, or to the, not the public, but sort of the stakeholders. It would be a publicly accessible web-based tool, such as this is an example of a Nature Conservancy web-based tool where we're publishing data that this one happens to be sea level rise and marsh migration, but it's a sort of simple to use targeted web map that answers a particular question and isn't sort of a you throw all the layers on kind of tool. It's a very targeted, easy to use, kind of nice to look at, and it'd be great if in a year, maybe two, we could get to this with the floodplain mapping and attenuation benefits. So, to wrap up, just a couple of quick observations on what helps make a science outreach tool like this effective and worth doing. So, a lot of these may sound like common sense, and maybe they are common sense, but I think they're worth saying anyway. Bring in partners and experts early in your project. If you want to get buy-in from folks, you need to have them in on the process early. Know your audience and where they're coming from. Try and get really clear on the questions you're trying to answer and the processes you're trying to influence. Is it a funding source, conservation funding source process you're trying to answer, or a conservation planning process, or a regulation process? And if this is pretty straightforward, but if you're creating a web app that includes a map, make it really simple to use and nice to look at. And don't end your project by just sort of putting your data and your results out there. You've got to really help people learn how to use the data and conduct outreach. And we found it really effective with this marsh migration tool to actually go visit towns, demonstrate or towns and land trusts, actually demo the tool with them and talk about their particular area and what the data and the results might mean to them and how it could be used. And I think that's a really important point and should be built into sort of, if you're thinking budget, you need to build in what you might think of as sort of extras on the end of your project. I think it has to be built in your budget from the beginning. That is all I have. I'd be happy to take any questions. Yes.
This isn't exactly a question, but one of the things you didn't mention was that Nature Conservancy, somewhere they have this humongous list of gazillions of people who they think might be interested in issues, and somehow my name got on the list. And they frequently send me these very helpful, informational, emails, and that this humongous web presence, this humongous newsletters and stuff are very and they're in non-scientific talk. They're in talk that regular people can understand. So I just wanted to mention that's another wonderful thing that your Nature Conservancy does well.
Great, thank you. I'll let our communications person know that we appreciate that. Yeah.
So after you've done this watershed, what's your level of confidence or enthusiasm about doing whatever other one is? Is it going to be an equal amount of time, or do you think you've worked out a method that's going to be allowed?
That's a good question. So competence, I don't know. Enthusiasm, I'm pretty enthused to see how different a sort of topographically and maybe geologically and soils how a different watershed performs. As far as time goes, the methods I worked out and all the scripting I did is done, and I can just apply that to this new watershed. The thing that will take time is I know all those thresholds for all the different size streams and their sort of cost surface and elevation stuff is going to be different. And so, yeah, it won't take nearly as much time as the first watershed, but it's going to still take a chunk of time to do, yeah.
I was curious about, the manipulations you needed to do with
Yeah.
the roadways
Yeah.
and the culverts,
Yes.
because you showed one that had two.
Yeah.
And so many roads have one or very small. I'm just wondering about the capacity of the flow of water
Yeah.
and how that might get integrated into your modeling.
So you're absolutely right. The culverts vary so much in their capacity to pass flow and whether it's adequate or not. And we have a ton of information about that. I did not build it in at this point. This was just creating a path in the elevation data for flow to happen without regard to how much flow was flowing through there. So my sort of cut through that road where the culvert was simply like a 1 pixel wide cut. It didn't build in any characteristics of the culvert that was there, but that's a really interesting thing that I think is worth checking out. Sort of the adequacy of the culverts in the whole system to pass the flow that they encounter. Yeah.
Well, speaking of sort of special tweaks to
Yeah.
your system, I'm wondering if it would allow you to deal with rivers that flow backwards, because they
Right.
here that does that. In some case, stream during a flood event on the canal drive. In some case, flows backwards, and in some case, narrows becomes a big lake.
Yeah.
And a new outlet comes around the backside of it, almost incorporated into an island. I mean, it's just a really interesting thing, and I'm wondering if that's the sort of thing that you could handle easily.
The way the model is written, it actually does handle it. That flooding of the surrounding lands doesn't depend on flow direction. So once you have those stream and river flow lines down, the flooding up onto that slope cost surface doesn't depend on direction. So even in places where it's not flowing backwards, if you get a sort of large river that's coming down, you'll get the cost surface, the sort of allowed flood cost surface, creeping up smaller tributary streams where you know the water's not, and it's sort of realistic. I mean, that can happen, but yeah, it's not tied to flow direction, so you can get that effect. But it's interesting. Yeah. One thing I'd like to experiment, if there's time and a need, is incorporating some sort of. So this is totally elevation model based. Be great to incorporate like soil porosity, some factors in the soil into this to get a better floodplain model.
So I was going to ask, you talked a lot about bringing in experts and partners early. What do you know so far about key decision makers or stakeholders interest in using this, how they might use it, when they use this kind of information to make decisions, when they don't, either from your work or anybody else's? Like, what have people learned so far that might, because you talk about pilot watersheds, but you might think about pilot decisions that you'd want to kind of align your work with?
Yeah, that's an excellent point. So we haven't had a whole lot of meetings with potential decision makers yet. We met with the Cumberland County Soil and Water Conservation District just to sort of feel them out on this project. And we met with the director, Robin, and she was pretty excited about it. We did not talk really specifically about what sorts of decisions she would be interested in using this type of information for. I mean, she was excited to have it. We talked about some potential applications, but didn't get into specific decision points. But I think that should drive a project like this. Start with what sorts of questions people will want to answer with your information and let it flow from there. So it's pretty important.
Any other questions?
Yes.
Has there been any history of this type of data being used to stop any development from happening on one?
Gosh, I don't know. So there's certainly GIS data out there that is used in regulation. So the NWI wetlands are used to create, zoning maps where development can occur, and there's Surveyed vernal pools are mapped, and development is regulated around those. And there are rules, and this is a question I have moving forward in this project, is suppose we find a really important floodplain that's providing a lot of attenuation service. What's the threat to that floodplain? So if it's in really good shape now and it's producing this service, but it's not threatened by development, maybe because there are adequate rules in place, and that's a whole area that we need to look into. Yeah.
Let's thank Dan again for